Okay, this is Dr. Matthew J. Trom. This is heat transfer. We are in a new module now, which is heat exchangers. Originally, I was going to do this entire lecture all just in one fell swoop, but the last lecture I gave was like 2.5 hours long, and so I'm amazed if anybody actually sat through the whole thing. And so this one was starting to get kind of long and painful, and so I decided to break it up into two. So we're going to talk today about log mean temperature difference, and then in the next lecture, we're going to talk about the effectiveness NTU method for heat exchanger analysis. So for LMTD, log mean temperature difference, if you could please read in the book. Chapter section 11.1, 11.2, and 11.3. That three sections will cover the content of this lecture. And then for those of you who are looking for the ADA compliant version with the transcription, when I finish this video, I will then have a transcription, and I will put the link here to access the video with the transcription so that you can get that if you need it. Okay, so let's jump in. As you know by now, I try to start all of my lectures with a meme or a cartoon, something relevant. And so this one popped up some time back on my social media, so we could see it's kind of Mickey Mouse, right? But you guys have already seen heat exchangers in thermodynamics, at least in theory, you have. And those were like pretty easy problems, right? Because you just applied the first law of thermodynamics and out popped the right answer. In heat transfer, as we will discover, heat exchanger problems are a little bit more nuanced and complicated. So hence the ripped Mickey Mouse here, as opposed to the kind of cartoonish Mickey Mouse that clearly had something dropped on his head for kinds of problems that we're going to deal with. Okay, so let's first talk about what a heat exchanger actually is. So the goal of a heat exchanger is to exchange heat or thermal energy between two fluids. They have to be at different temperatures, right? Because you need a temperature gradient to change energy, thermal energy. And typically the fluids are at different pressures. We don't have time to talk about it in this class, but you will discover later on in your lives as engineers that like the absolute best way to like do heat transfer between two fluids is to just mix them, right? That's like the most quick and efficient way to achieve a target temperature. But a lot of times in mechanical engineering, chemical engineering processes, your process fluids are at different temperatures, or they're chemically insolvent with each other, and so you do not want to mix them for various mechanical or chemical reasons. And so it's typically you've got fluids at different pressures that are separated by a solid wall that are exchanging heat with each other but don't actually mix. And so that arrangement is typically called a heat exchanger, which is what we're going to talk about in this lecture. Um, okay, so the simplest heat exchanger, at least that I can think of, is one where you have a hot fluid and a cold fluid, and they're moving together in concentric tubes. And so I show two possible arrangements for that here. And so we have a so-called parallel flow heat exchanger. And what characterizes a parallel flow heat exchanger is that the hot, there we go, hot and cold fluids enter at the same end. They flow in the same direction and they leave at the same end, right? So if we're imagining just concentric tubes, as I've described here, we have, tube in the middle, tube on the outside. And so this is sort of the axial view. And then these are the edge-on views, right? So my concentric parallel flow heat exchanger, again, has everything entering basically from the left and then exiting basically from the right, or top, bottom, but the bottom's on the left and the top's on the right, right? So anyway, that's parallel flow. But the whole point is that the fluid is moving in the same direction. In a counterflow heat exchanger, we also have hot and cold fluids. and these enter in opposite ends or at opposite ends, and they flow in opposite directions, and then leave at opposite ends, right? So we've got the inner tube, the fluid flowing from left to right, and then the outer tube, we have fluid flowing from right to left. And so hence counterflow concentric heat exchanger because fluid is flowing in different directions. Okay. Um, so there are many, 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 many types of heat exchangers. So let's just run through several different examples that you'll encounter in both the book problems and your future lives as engineers. So we have cross-flow heat exchangers. There's two primary configurations that are differentiated by um, basically whether there are fins or not. And it's kind of a weird terminology that's used to describe this. So if you've got a series of tubes that are carrying fluid, and then you've got cross flow over those tubes, but that cross flow is kind of mitigated by these plates or fins that are put in place. That is so-called unmixed flow. Unmixed because the plates basically prevent the fluid from the cross flow fluid, right? The fluid on the outside of the tubes from propagating at all in the direction of the tubes. It's like pure cross flow with very little mixing in the axial tube direction. So I say that these are finned cross flow heat exchangers with both fluids unmixed owing to fins inhibiting traverse flow, right? So fluid going this way is unmixed, and then obviously fluid going this way into the page is unmixed because it's being carried in these tubes, right? So that's one type. Another type of cross-flow heat exchanger is one that has a similar geometry in terms of the tubes, but it does not have the fins in the cross-flow direction, right? And so this is a so-called unfinned cross-flow heat exchanger with one fluid mixed and the other fluid unmixed. The unmixed fluid is still the one that's traveling through the tubes, right? There's no way for fluid in two of these different tubes to coexist or commingle or commix with itself. But the fins that we had in this configuration are gone in this configuration. And so the fluid can actually move into or out of the page if it so chooses, and it can mix. And so that's called one fluid mix, right? So that's where that comes from. Okay. Um, Another very common type of heat exchanger is a shell and tube heat exchanger. These are kind of a broad kind of category that describes um, all of these different arrangements where we have fluid entering and then passing through tubes, and then having the fluid that um, enters in the like outer skirt, passing through the so-called shell. I've got it the wrong way. There we go. Here it is. It's entering here and it's leaving here. And so this is like sort of counterflow, right? Because we've got the fluid entering the inlet fluid here entering from the right and traveling through the tubes and then exiting to the left. And then the fluid in the shell, we have that entering more or less from the left and traveling to the right. And then there's an additional feature, which is called a baffle, right? So I say here, baffles increase the shell side fluid convection coefficient by inducing turbulence and cross flow velocity component relative to the tubes. So these lines are representative of baffles. They're just like physical separations or physical barriers that force the fluid on the shell side. Instead of just kind of traveling straight in the axial direction down the shell, it actually has to take this much longer, more tortuous path through the baffles. And that, of course, induces more mixing, larger heat transfer path, better heat transfer. And so baffles, even though they do create some modicum of pressure drop, usually more than make up for it in terms of energy savings from the beneficial effects of heat exchange between the tube fluid and the shell fluid, right? So typically you see baffles in a shell and tube heat exchanger. So let's see. Oh yeah, so I say here the simplest form involves just one tube pass and one shell pass, which is what I show here, right? So fluid enters, goes through one tube pass and exits. Fluid enters, goes through one shell pass and exits. Doesn't need to be that way. It can be more complicated. I'll show you that on the next slide. But this is kind of the simplest version for me to show you. And this shape might look familiar to you. You guys have seen this icon on the bottom left. I put it here just to kind of remind you that you've seen this, for example, on the Canvas site for the course. So this is the course icon, but I purposely made it look like a shell and tube heat exchanger. Right, so you could actually see like the gradients in temperature. The hot tubes are in the middle, right, and getting hotter and then progressively cooler as they move from left to right, and then the fluid entering here, getting progressively cooler as it's moving from right to left. So you guys have seen this. Just wanted to point out that the icon for the class is actually meant to be a shell and tube heat exchanger, right? So it's like, what is this thing that Trom has put on the Canvas site? Well, now you know what it is, right? So it's a heat exchanger. All right. So I mentioned this is one type. So this is a shell and tube heat exchanger with one shell pass and one tube pass. We've got cross counterflow as a result of the baffles, but you can have more complicated arrangements. So I already mentioned what baffles are. So this is a shell and tube heat exchanger with one shell and two tube passes. So what's happening here is the fluid enters, it gets to the end of the heat exchanger, and then it turns around and comes back the way that it came in, it's a linear parallel path, and the outlet is on the same side as the inlet, but then this one also has these baffles built in, and so you can see from the inlet of the shell that same kind of tortuous path that the fluid on the outside of this now two tube pass heat exchanger operates to provide heat transfer. This can, of course, get even more complicated, right? So here I show a shell and tube heat exchanger with two shell passes and four tube passes. So it's essentially like this doubled, right? So you can see the fluid coming in, right? Turning 90, 180 degrees, and then turning another 180 degrees, and entering another shell, and then turning again and coming out. So that's the pathway that this guy takes through this geometry. And then the shell fluid comes in at the top. The baffles cause it to kind of undulate up and down, like with the other cases, and so it moves across the shell side, and then it passes from the top shell into the bottom shell and continues to move through the shell side and to the outlet. Right, so that's two shell passes and four tube passes. Like I said, this can get like arbitrarily complicated with multiple tube passes and multiple shell passes, but these are kind of the lower level arrangement. So I wanted you to see these just to get a sense of what they look like. Okay, so there's additional heat exchanger types, so-called compact heat exchangers. You guys that did the Sandvik project with the oil cooler, you encountered these, right? Because we didn't know at the time, right, how to deal with heat exchangers, but we definitely know how to deal with fins, and you guys designed all kinds of interesting fin geometries. So that was basically a type of compact heat exchanger that you guys were analyzing. So the benefit of a compact heat exchanger is that they have these very large heat transfer surface area per unit volume numbers. And it seems like a really weird unit to use. But we're looking at something like 400 meters squared per cubic meter for liquids, and then about 700 meters squared per cubic meter for gases, established through kind of using these plates as fins. But why is this unit weird? It's weird because it's like an area divided by a volume, right? And your natural instinct is just to cancel out the meters and just report this as one over volume, one over length. But it actually makes sense because if you think about what you're trying to do with a compact heat exchanger, you're trying to cram as much area as possible, as much heat exchange area as possible into as small a volume as you possibly can. And so this metric of area, this is heat exchange area over total volume, heat exchange area over total volume, actually makes sense as a figure of merit or a metric for compact heat exchangers, where you're trying to basically make them as small as possible and still enable, when I say small, volumetrically as small as possible while still trying to enable enormous, very high rates of heat transfer. So hence the very weird units, meter squared over meter cubed. Um, so I say here, dense arrays of fin tubes or plates are typically used when at least one of the fluid is a gas. We've already talked about why that is, right? Because the convection coefficients are far lower for gas than they are for liquid. And so you typically put the fins on the gas side to kind of offset the fact that you've got lower convection coefficients, and you don't end up with a bottleneck in your heat transfer process. So at least one fluid is gas and hence characterized by small convection coefficient. Okay, I pretty much just said that. So here's a couple of arrangements. They're all very similar. So we have flat tubes with continuous plates that are acting as fins in a compact heat exchanger. Right here, we've got basically the same arrangement, except instead of square passageways for the fluid, we have circular passageways for the fluid, right? So this is circular tubes with continuous plate fins in a compact heat exchanger. And then this third one is just a variation on the second one, which is instead of having the fins all kind of attached to each other as plates, we adopt a more kind of circular cylindrical type geometry, and we have circular tubes with circular fin tubes in this compact heat exchanger arrangement, right? So just different configurations for you to be familiar with. There is yet another type, which is, I say here, parallel plate heat exchangers may be finned or corrugated and may be used in a single pass or multi-pass configuration. So these are compact single pass plate fin heat exchangers where you can actually see the corrugated fins, right? So corrugated fins here, corrugated fins here. In this case, on the left-hand side, the fluid is just making one pass, right? So you basically pressurize this face and the fluid runs into the page, and then you pressurize this face here to the left and the fluid runs through the page, not through the page, but sorry, like, what am I trying to say here? Perpendicular to the page. Yeah, that's what I want. Perpendicular to the page. The hallmark of this guy is that the fluid just goes through once and that's it, right? Here we have a compact multi-pass plate fin heat exchanger where it's specifically designed so that the fluid enters from the bottom. This is cut away so that we can see it, but the fluid gets to the other end and then it gets turned upwards and it comes back towards us, and then it gets turned upwards and reinserted into the corrugated fin array. And then the same is true in the cross flow direction, right? So the fluid comes through this way, and then it goes through this way, and then it goes through this way, and so forth. So that requires a little bit more plumbing, but just an equally valid and legitimate heat transfer geometry. So I say here, compact heat exchangers, flow passes. This probably should say passages, flow passages. Are typically, let me just make a quick note so I can fix that. There we go. Okay, typically small. So a hydraulic diameter of less than 5 millimeters. So the resulting flow is typically laminar. So you guys have played with these a little bit with the Sandvik project, right? So people put in their designs turbulators to mix up the flow. Try to get the flow to go through faster to force a transition to turbulence, to increase the convection coefficient. So yeah, I mean, these are just by nature very small, and so typically laminar flow, unless something spectacular or unusual is happening to drive the Reynolds number way up. Okay, so now that we've talked about the different types, at least some of the different types of heat exchangers, let's talk about overall heat transfer coefficient, which is going to be one of the things that you're going to end up solving for a lot when you're solving these heat transfer problems. So good to know what this is. So I say here, overall heat transfer coefficient, which we'll use the variable capital U, which is also what the book uses, is defined as the total heat transfer thermal resistance between the two fluids, right? Remember, two fluids separate, I've got it shown here, two fluids separated by a wall that facilitates conductive heat transfer across it. So we've got hot fluid on one side, we've got cold fluid on the other side. You guys remember this from composite walls, right? We did this a little while back. It's the same idea, except now instead of calculating a sum of resistances, we're just calculating this thing called U, which is basically just a sum of resistances. It's the exact same idea. It's just written, as I am so fond of saying, in kind of a law of conservation of chalk form, just as a single variable instead of a sum of multiple resistances. So here's the equation, right? So Q dot, which is heat transfer, is equal to U times A times delta T, right? It looks very much like a conduction equation. And then just like we can do with all of our other heat transfer equations, we can come up with an equivalent resistance. So if you ever wanted to write this in terms of resistance that you could then use in a one-dimensional heat transfer model, you just say that the resistance is equal to 1 over UA. And we can then use all of our resistance rules from circuits class and physics and so forth to figure out what this U value is. So for a wall separating two fluid streams at different temperatures, we have hot fluid on one side, we have the conductive wall that's separating the hot fluid from the cold fluid on this other side, and we have a heat transfer process from the hot side to the cold side is indicated by these arrows. And so, what is that heat transfer process? Well, it can be represented as the temperature difference between the hot fluid and the cold fluid, separated by three resistances in series: the convective resistance in the hot fluid, the conductive resistance through the wall, and then the convective resistance on the cold end. So three resistances to heat transfer. Okay, so we know how to represent that using our resistance model, right? So from circuits. So R, which is the equivalent resistance, is just RI for inner plus R wall, right? Which is the conduction through the wall, plus R outer, which is the convection coefficient for the wall here, or based on the convection coefficient for the wall. And so these are those terms, right? So R sub I, inner resistance, is 1 over HIA, so the convective heat transfer coefficient on this side of the wall. And then, of course, we have the thermal resistivity of the wall itself, right? So just the thickness of the wall divided by Ka. K is the thermal conductivity, and A is just the total area across which heat is transferred. And then we have R naught, or R, I should say R O, I think, for outer, which is here. And we're going to have 1 over HOA. HO is a convective heat transfer coefficient, and A is that same cross-sectional area that we keep encountering over and over again, because this is basically a slab, right? Euclidean geometry. Okay, you can also write the equivalent resistance that'll end up becoming U for cylindrical geometry, right? And you guys are familiar with this from like chapter 2 and chapter 3. So we're going to have hot fluid running through the center. It's going to be separated from the cold fluid by this pipe wall, and that pipe wall is going to present some resistance to heat transfer that we want to account for in our model. So here we have the inner resistance, right? So the heat transfer resistance between the fluid itself and the inner wall is 1 over HIAI, right? So these are heat transfer coefficient internal and area internal to the wall. Our wall is just, right, this is a cylinder, so we're just going to use our cylindrical resistance equation. So there's that. And then outer is 1 over H outer times A outer, right? Same 1D resistor model. It's just these resistors, particularly the one associated with the wall, are represented in cylindrical coordinates instead of X, Y, Z Euclidean coordinates. But otherwise, it's the same. And you guys have seen this before. So hopefully that feels like a review. Okay. So the overall heat transfer coefficient is defined as the total heat transfer thermal resistance between the two fluids. We talked about that. For the cases that I just talked about, where I have just a conductive wall separating the two fluid streams, nothing more complicated than that. I can write 1 over UA. And it turns out that 1 over UA is equal to 1 over the UA associated with the cold side, which is also equal to 1 over UA, which is associated with the hot side. Right? And these are the same. You can actually see it in this equation. These are the same because the heat flux is the same from the hot fluid into the cold fluid. The temperature difference is the same at whatever spot you're analyzing. And so UA has to be the same. And what will end up happening, we'll see, if the areas are the same, the U's themselves are the same. But like, for example, we'll get to it down here in cylindrical coordinates, it's possible that the cross-sectional areas are substantially different, in which case, even though UA is equal to UA, U itself might be higher and A might be lower versus U being lower and A being higher. But when you multiply them together as products, they come out to be the same. Okay, so we've got our equivalent resistance 1 over HA for the cold side, our equivalent resistance 1 over HA for the hot side, all summed together with the resistance of the wall, right? And of course, the resistance of the wall is a slab, right? So you guys know how to deal with that. We do have some subscripts that we have to keep track of. So I think I started to mention this, but C is for the cold side and H is for the hot side. So C and H refer to cold and hot fluids respectively. Calculations of UA do not require you to know the hot versus the cold side designation because, as I just mentioned, UCAC is equal to UHAH. So provided you know, just one of those values, so I should say one of the sides, right? So UCAC or UHAH, you now know everything about the other side, and can also determine the resistance. Right. Okay. And then here is that same equation for UA, but just for cylindrical geometry. And this is an unfinned heat exchanger tube that we're talking about, right? So everything is the same with the exception of the heat transfer through the wall. And as a quick aside, the wall is usually very thin and made out of metal, right? So very conductive. And so sometimes just to make the math easy, engineers will just drop this middle term, especially if it's small compared to the other two terms. So just wanted to mention that. Okay, so just like with chapter 1, we want some place where we can get like a sanity check to make sure that once we've done the math, the resulting number makes intuitive sense. And so the book gives us table 11.2, representative values of the overall heat transfer coefficient. And so you can see the various fluid combinations, water to water, water to oil, steam condenser with water in the tubes, ammonia condenser with water in the tubes, alcohol condenser with water in the tubes, and a fin tube heat exchanger. Several different values and relatively, or I should say several different values and viable ranges for U given in this table, right? So just good to come back and check if you do a calculation to find U, you've got this table, so it doesn't hurt to check to make sure that you've got the right order of magnitude. Okay, so let's kind of ratchet it up here and start to make things a little bit more complicated by bringing in some kind of more realistic features and attributes for heat exchangers. So the equation that I just showed you applies to a brand new, clean, unfinned surface. However, during normal heat exchanger operations, surfaces are subject to a phenomenon called fouling, which is where impurities that are dissolved in the fluid will come out of solution and actually like rust or deposit themselves on the inner wall of the shell and the outer wall of the tubes. Sometimes the inner wall of the tubes, if you've got kind of a solvent carrying liquid running through the inner tubes. But these surfaces basically tend to um, rust, right? And or be affected by some sort of chemical reaction that then builds up this layer of like scale, right? Which then induces its own separate heat transfer resistance, which reduces the overall effectiveness of the heat exchanger, right? And you can see here, right, this is a picture taken on purpose, right? The left side is a heat exchanger that was allowed to run for probably several years in some, relatively dirty process where there was, probably solids dissolved in whatever liquid, maybe water that was running through this thing, and they came out of solution as the fluid cooled. And now, if you take a cutaway of the heat exchanger, you can see that it's a god awful mess on the inside. This is what it looked like new, right? So new pristine heat exchanger without any fouling versus on the right here, a heat exchanger that's, had a good service life, and now definitely subject to the ravages of fouling. So how do we, in the equation that we had, how do we deal with fouling if we suspect that it is reducing the effectiveness of our heat exchanger? So fouling is modeled by introducing an additional thermal resistance. So it's kind of like contact resistance in that regard. Those are called fouling factors, which are represented as R sub F double prime. Um, the value of this new resistance that you're going to add into your heat transfer model really depends on operating temperature, fluid velocity, length of service of the equipment, all kinds of factors that you don't really have any control over, and a lot of times aren't even mentioned in the book. So a lot of times you'll just be given a value, or you'll be given enough information to find a value from a table. Um, Another thing that often happens with heat exchangers, because we want, large surface areas as large as possible, but still with a compact form factor, is engineers will often add fins to the inside of heat exchangers to increase the surface area, and reduce the overall heat transfer resistance. And so what I show here is kind of the complete version of this equation, right? Where we've just got um, here, it shouldn't be out. This plus sign should not be there. I just noticed that. It's the version of this equation that includes fins and fouling, which is this, right? So 1 over UA for the heat exchanger is 1 over um, eta not HA for the cold side, plus the fouling resistance over eta naught A for the cold side, plus the resistance presented by the wall, plus the contact resistance or the fouling resistance for the hot side, and then 1 over eta times HA. I'm noticing this should actually be H. So we'll fix that for the hot side. Right. So all I'm doing here is just taking this equation and just adding the ability of that equation to account for fouling, right? So I'm just adding a resistance associated with fouling, and for it to basically deal with fins, right? So if I wanted to put extended surfaces on these tubes to give them more surface area to facilitate heat transfer, that's what this eta is for, is to provide that extension. Okay. So a little bit more about fouling and fins. So here are just some typical values for what you might expect as fouling resistances in heat exchangers, subject to these different kind of processes in industry, right? So we've got seawater and treated boiling feed water. We have an associated resistance for that. Seawater and treated boiling seawater and treated boiler feed water. Huh. Interesting. These look the same to me, although this is a table right out of the book, copy pasted right out of the book. My guess is that one of these is treated and the other one is untreated. So let me check on that. And I'm also realizing I've been talking this whole time without my laser pointer. So hopefully now you can see my pen. Okay, so that's sort of funny because these I think are the same, and this comes right out of the book. While I'm sitting here, let me actually look at the book and see what the book says. Seawater and treated boiler feed water, seawater and treated boiler feed water. Yeah, okay, these are the same. Not sure why there's two different values, but this book is special. Okay. River water, we have a range there. Fuel oil, we have a value there. Refrigerating liquids, we have a value there. And steam, non-oil bearing steam, we have a value there, right? So if you're um, using this equation and you suspect fouling and you don't have really any information except for the types of fluids that are running through your heat exchangers, you can go to this table and hey, if you have seawater and treated boiling feed water, you can use either one of these values because apparently the different values for the same fluid. Okay. So let's talk a little bit about fins since we've talked quite a bit about fouling. So there's this quantity eta naught, which is termed as the overall surface efficiency, and it ends up getting used in the heat transfer rate equation, just like we did with fins, where we have the total heat transfer is equal to this term eta naught times H times A times temperature difference, where the temperature difference is the base temperature minus T infinity. So that's at temperature in the free stream. So you've seen this before. And then when we're talking about fins, and then we're going to define eta naught as 1 minus AF over A times 1 minus eta F. And what are all these things? Well, AF is the entire fin surface area. So just the surface area of the fins, not any of the kind of metal that's separating the two flows from each other that is not a fin, right? So that's A, which is the total surface area. So that includes both the fins and all of the non-fin surface area where heat exchange is occurring. That's just capital A by itself. And then eta F is the efficiency of a single fin, which you guys know how to calculate since we just did that chapter. Okay, the book gives kind of an extra rule of thumb, which is ooh, excuse me, they say if fouling is significant, then you want to replace H in this equation. If you're trying to calculate the heat transfer, you're going to want to replace H with the so-called partial overall heat transfer coefficient, which is just capital U with sub P for partial. And the equation there is just H divided by 1 plus H multiplied by whatever the fouling resistance is for your particular arrangement. So this just modifies H a little bit to account for the fouling. Okay. Yes. So now that we've talked about all the various kinds of heat exchangers, we've talked a little bit about how the equation to find U works and how that equation can be modified to account for fouling for long service life heat exchangers that have got some scaling built up, and for heat exchangers that have fins or other extended surfaces. And so we're now going to start talking about solution methods. There's two of them. The first one is called LMTD for log mean temperature difference. That's what we're going to talk about in this lecture. The other one is called the effectiveness NTU method, or effectiveness number of transfer units method. And that one is that's the subject of the next lecture, right? So we're going to talk about LMTD now and effectiveness NTU next time. I did actually, so I'm pretty sure this image is AI generated. I did not generate it. I actually found it as I was kind of hunting around for kind of rule of thumb for when you would use LMTD versus when you would use effectiveness NTU. And this popped out of like an open source heat transfer website. So I quite like this. And I think it's right? It actually came out of a website instead of just out of AI. So I think somebody vetted it. So the ultimate question is when to use each one of these approaches, LMTD versus the effectiveness NTU method. And I'll go over it again here, but just so that you can see it kind of in this beautiful AI generated graphic form. You use LMTD when the basically everything is known. The inlet and outlet temperatures are known, and you're essentially doing a heat exchanger design process where you're trying to figure out the appropriate U and the appropriate A to get the amount of heat transfer that you want. So it says here, you use LMTD when you basically already know the answer. And by knowing the answer, that means you know all of the inlets and all the outlets. So that's what I say here. Use LMTD when the following are known or can be calculated. So M dot C is the mass flux of the cold stream. M dot H is the mass flux of the hot stream. Uh, TCI, this is the cold temperature of the inlet. TCO, this is the cold temperature of the outlet. TCI, this is the hot temperature of the inlet, and THO is the the hot temperature of the outlet. Yeah, of the outlet. So if you know all those things, you can basically, and I'll show you an example, you can plug them in and you can find UA that's required to achieve these conditions. And then that guides your design process, right? So it's like, what is it that we need to actually design? Well, it needs to have a UA of this, so we're going to design it appropriately. So that's LMTD. That's what we're going to do for the rest of this lecture. The next lecture is going to be effectiveness NTU, and that's the one that you use when you know the following. So you usually know UA, you know the mass flow rates, um, and you know the temperatures at the inlet, or inlets, I should say. So the cold and the hot inlet, but you do not know the temperatures of the outlet, right? So oops, this should say. Let me make a note to myself. This should say T cold outlet and then TH outlet. I copy pasted from here to here. I forgot to change this. So TH outlet. Um, the heat exchanger outlet conditions, right? So there's no way to get to these using LMTD because you're in a situation you've got too many unknowns. You can iterate to get there with LMTD, but effectiveness NTU is way easier, right? It's just a straight shot, straight all the way through without any iteration or coding. So we'll do that in the next lecture. So right now I'll focus on LMTD. Okay. So I am going to, let me just make sure. Yes, okay. I am going to walk through this one time. It's described in the book. My normal philosophy is, it's not super important for you to know how the sausage is made as an undergrad mechanical engineer. So long as you know how to use the end equations, that's really the most important thing. But there's kind of enough weirdness and nuance with heat exchangers, particularly with the effectiveness NTU method, that I think it's valuable to go through one time how all this is derived. And once you've seen it done, right, and know where it is in the book, if you forget, you can always go back and look it up later. But if I never covered it and you encountered something a little weird in future problem or homework or something like that, quiz, you'd sort of be like in the dark about where the equations came from. So I'm going to break my own rule and I'm actually going to walk through the derivation just so that you've seen it done once. Okay, so we're going to consider two fluid flows at different temperatures that are in good thermal communication across a conductive wall, right? So basically a heat exchanger. And we're going to apply the first law of thermodynamics, the energy balance, to both flows. So you can see here, I've got my control volume for, it looks like this is the hot fluid. And then here, I've got my control volume for the cold fluid. Oh, sorry. I have, since I've got hot fluid on the top, cold fluid on the bottom, I've got some transfer of heat between them. That's Q. And then, so Q leaving the hot fluid and entering the cold fluid, same Q. And then I've got this thing all nicely insulated so that heat transfer internally between the two fluid streams is the only one that I need to worry about. Okay, so how do I find this Q that's leaving the hot fluid and entering the cold fluid? Well, that is just the if I apply the first law to the control volume, it's just m dot of the hot fluid multiplied by the enthalpy of the hot fluid at the inlet minus the enthalpy of the hot fluid at the outlet, right? So the hot fluid is dumping its thermal energy overboard, right? So this enthalpy, which is linked to temperature, is going to be higher than this enthalpy. So this is going to end up being positive, but leaving the system. And then for entering this colder fluid at the bottom, it's basically the same idea. So m dot c is the mass flow rate of fluid through the system. And then I've got the enthalpy of the cold fluid at the outlet here minus the enthalpy of the cold fluid at the inlet here. And the reason that I have it that way is because, right, the cold fluid is picking up thermal energy. And so this gives me a positive number, right, by outlet minus inlet should be hotter over here than it is over here if this is working correctly. So I'm going to put the positive value there. So just to remind you guys about the subscripts, I already kind of said it, but just so that you can hear me say it again. I, in this case, is the fluid enthalpy. Don't know why our book uses that variable. I think it's a really silly choice because I shows up, you can see like inlet, right? It shows up in like iterative, like I equals 1, I equals 2. So I don't know why they use I, but they do. So I try to use I just to be consistent, at least in this class and with this book. So that's what I means. The subscripts H and C refer respectively to hot fluid for H and cold fluid for C. And then the subscripts I and O designate inlet and outlet, right? So I is inlet and O is outlet. And this is that really bad kind of notation mismatch where you've got the enthalpy as I and you've got the inlet conditions as I. And man, I wish they used a different variable, but they don't. So again, try to be consistent. Okay, so if we make some assumptions, right? So remember that enthalpy is equal to C or CP T. So I say here, fluids are not changing phase and specific heats are assumed constant, right? So that specific heat is constant despite the change in temperature of the fluid as it's moving through this process. At least that's an underlying assumption. And also the fluid is not changing phase because that's a totally different process. Then I can rewrite these expressions in terms of temperatures, which is what I really want, right? Because this is heat transfer. We're interested in temperatures, not enthalpies. And so the heat transfer, which is going to be the same from the hot fluid into the cold fluid, is m dot h Cp of h multiplied by h at the inlet minus h of the outlet. By the same token, that same Q is mass flux of the cold fluid times Cp of the cold fluid times the temperature of the cold fluid at the outlet minus the temperature of the cold fluid at the inlet, right? And these are reversed on purpose because this one is rejecting heat, right? Rejecting heat, yes. And this one is absorbing heat, right? So hence these guys are switched to make sure that these are the same sign. Okay. Let's see. Let me just read this one. It says where temperatures in the expressions. Oh, yes. Okay. So things are about to get more complicated. So these temperatures here in the expressions refer to the mean fluid temperatures at the designated location, right? We have not yet talked about convective heat transfer, but when we do, you will realize that if I'm dealing with a fluid that's moving through a pipe, there is a temperature profile on the tube, right? So it's actually potentially colder on the edges than it is in the center or vice versa. And these temperatures do not account for that kind of pipe scale temperature gradient. These are just average temperatures across the entire diameter of each one of these pipes. So just be aware of that as the derivations continue to advance. Okay. So we have these expressions for heat transfer from the hot fluid to the cold fluid. This is good. These expressions arose from the first law of thermodynamics, and they are completely independent of the heat exchanger geometry, right? So notice there's no U, there's no A, right? Nothing about the heat exchanger geometry is in any of these equations. That'll end up being very useful for later because we're going to end up having to solve for For example, they'll give us three of the four temperatures and ask us to solve for the last one, and then they won't give us any geometry, right? But it doesn't matter. You don't need the geometry, right? You just set these equal to each other because they are equal. And if you know the mass transfer, mass flux rate, and the specific heat of the fluids, you could calculate what that last temperature is, right? So we're gonna using that in the example that I'll give you at the end. Um, so, okay, just want to point out that they're independent from heat exchanger geometry. Um, so we need an expression that considers the geometry, right? Because we're actually interested in calculating U and A um, to figure out what's going on inside the heat exchanger to make sure that it's been designed correctly. And so the initial expression that we might come up with is to say, okay, I'm going to take a little section of this tube and I'm going to call it delta X in terms of thickness, and in terms of the size, it's the same size as the channels. And it's trading heat with an identically shaped and sized um, control volume on the other side, the cold side of the fluid. And as this thing like marches down, so I'm going to follow it, right? Like Lagrange, I'm going to follow it down the tube, and I'm going to track its temperature as it moves down the tube in the positive X direction, right? And all that is fine. But whoa, good luck with the math. But that's sort of the underlying idea. That's where we're starting, right? So this differential heat transfer from the top element to the bottom element in two different tubes at two different temperatures, thermally communicating across this area dA, surface area between the two tubes. So that heat flux is equal to U times dA times delta T, so the hot temperature minus the cold temperature. In this case, I represented U as a function of X. We'll find out later on that unless you're told otherwise, we just assume that U is constant. But I wanted to just to be clear in this slide that it can actually change as you traverse down the slides, just or down the heat exchanger. So just be aware of that, that U can possibly change. Okay. What's the challenge with this? Well, TH minus TC, the temperature difference that drives this heat transfer from the hot side to the cold side, that varies with position, right? As I'm moving down the heat exchanger, the hot stream is getting colder and the cold stream is getting hotter, and they don't necessarily move in tandem with each other. We'll see that in a second. Like one could get colder quite a bit faster than the other one gets hotter if they have different specific heats or different masses. So we need an appropriate expression. So I say here, however, TH minus TC varies with heat exchanger position. Therefore, we need an appropriate mean temperature difference. So it turns out that the appropriate mean temperature difference is just this one. So rewriting my original equation and just representing this representative temperature difference as delta T sub M for now, M for mean. Okay, so you might be asking yourself, okay, this is great, but what mean temperature difference is appropriate, right? There's all kinds of different definitions. This could be a median, a mean, an average, right? It could be an integrated average, it could be a summed average. Like, what is this thing? And what's an appropriate value and level of accuracy? Okay, so to attempt to answer the question of what's an appropriate delta T sub M, M for mean, let's look at the first example, which is a parallel flow heat exchanger. So in a parallel flow heat exchanger, we have our hot stream and our cold stream. And as we talked about way back here, right? Parallel flow concentric tube heat exchanger, the flow moves all in the same direction, right? So probably didn't need to go all the way back to show you that, but I felt excited to do that. Okay, so here we are. Right, so everything is flowing in the same direction. And what this causes is initially a very, very large delta T. Why? Because the hot stream is hot, the cold stream is cold, and as they move together, their heat exchange process draws their temperatures together. And so initially they're as far apart as they're going to be, and by the time they exit the heat exchanger, they're basically as close as they're going to be in temperature. So delta T is initially very large, but it decays with increasing X, ultimately approaching zero asymptotically, right? So if this were allowed to be really long, these two temperatures would basically become the same temperature if you had a really long distance for that. The other thing that I want to just point out, because I did it and it's a little, um, maybe distracting, is I've got these yellow dotted lines in here. That was just for me to line up the start of this figure with the start of this figure, just so that you could see that as you march through the tubes, the temperature of the hot side does actually cool down, and the temperature of the cold side does actually cool up. And they reach this very slight temperature difference at the end when they exit the heat exchanger. Um, okay. The other thing that I want to mention about parallel flow heat exchangers is that T cold of the, I should say T hot of the outlet, um, is always larger than T cold of the inlet, right? You can see that here, right? So here's T hot of the outlet. Here's T cold of the inlet. It doesn't matter how far I go, how long I make this thing. These two approach each other asymptotically. At an infinitely long heat exchanger, they're the same temperature, but always in the real world, T sub H at the outlet is greater than T sub C at the outlet. And we'll see for the counterflow heat exchanger that's different, but it's an important thing to know for parallel flow heat exchangers. I also want to mention that there's a subscript that the book uses, which is I like inlet and outlet because I think it's easier to keep track of. Sometimes the book will swap out inlet and outlet for one and two. So one and two designate opposite ends of the heat exchanger. You can see that here. The what I would call the inlet for both the hot side and the cold side is at station one, and then the outlet for both the hot side and the cold side is here at station two. So just be aware that when the book talks about the different streams, it will exchange or interchange inlet, outlet one and two with each other. That's very confusing, but that's their convention. Okay, so how do we analyze this to get to, remember, we're looking for an appropriate delta T mean to put into this equation to be able to solve for heat transfer. So we need about 5 assumptions that we have to apply to make sure that we can do the math accurately. So we're going to apply the energy balance to the hot and the cold fluid elements, like I show here, subject to the following assumptions. So one is the heat exchanger is insulated by the surroundings, which you can see here in this schematic. What that really means is that the only energy exchange that we need to account for is between the hot fluid and the cold fluid, right? So that's number one. Number two is that axial tube conduction is negligible. So what that means is the tubes themselves, right? The metal in the tubes that are carrying the heat, that are facilitating this heat transfer, carrying the fluid, facilitating this heat transfer, those cannot be such that they're facilitating axial conduction, right? In other words, if it's like hot, let's see, where would it be hot? If it's hot here and cold here, right, we do not have heat transfer, at least not by conduction, in the axial direction. That's what this one means. All the heat transfers through convection. Third is the potential and kinetic energy changes are negligible. We have flowing fluid. The chances of it going up a hill or down a hill or increasing in velocity or decreasing in velocity are non-zero. And so we want to put this assumption in there to make sure that you're not dragging around extra kinetic energy and potential energy terms that you ultimately don't need. We're going to imagine that specific heats are constant for both fluids throughout the process unless told otherwise. And we're going to assume that U, which is the overall heat transfer coefficient, is constant, regardless of what's going on in the heat exchanger, whether it's local temperatures going up or down. Okay, so with those assumptions, we're going to apply the energy balance to each of these elements, kind of similar to the way we did before. But these are now differential elements, not like complete pipes filled with liquid. We need that derivative in order to carry out an integration later on. So here is dq, which is equal to minus m of the hot side, cp of the hot side, delta th. So delta t of the hot side, And right, that heat flux is the same leaving the hot end as it is entering the cold end. And so that's going to equal MCCP DTC, right? So capital CH and capital CC are the hot and cold fluid heat capacity rates, right? So it's just MCP. Let's try again. M lowercase cp is just equal to uppercase cp. M dot lowercase cp is equal to uppercase c. So this is just law of conservation of chalk. I normally don't do this, but the derivation given in the book does it and like propagates it all the way through. So I'm going to keep it just to avoid confusion. Okay. Okay, so this is now the equation, right? So we've got differential heat, which is equal to some local U multiplied by dA, so the basically cross-sectional area through which heat transfers from the hot sphere or the hot uh, fluid element to the cold fluid element. dA is the actual area that it's crossing, heat transfer is crossing through. And then TH minus TC, these are local temperatures, right? So the local temperature at this spot where I'm doing the analysis is what we're talking about here. So I say this is the local temperature difference. So the derivative of delta T is just dTH minus dTC. And we're going to end up using that derivative to continue to push us forward towards this goal of finding the appropriate mean temperature to put into, where is it? So far back. Uh, well, anyway, we're looking for the appropriate, where did it go? Trying to find the appropriate temperature. Oh, here, the appropriate temperature to put in here. Right. Okay. Okay. So, we're now going to take this equation and we're going to combine it with this equation, and we're going to take a integral, right? So here I am basically setting them equal to each other, right? Moving everything to one side of the equation. That's delta t. And this step, let me see here. Oh, right. Okay. Right. So dq, right, is this, right? And so this thing is delta. Here it is. This thing is delta t, and so what I'm doing between this step and this step is I'm just substituting this equation in for dq star, or sorry, dq dot, and that gives me this guy. And then I'm taking the integral from station one, which is the inlet, to station two, which is the outlet, and then just letting the integral kind of do its thing. Um, Everything here is a constant. U is a constant, CH is a constant, CC is a constant. So that all comes out, and that just leaves the integral of dA on the right-hand side and the integral of d delta t over delta t on the left-hand side. And so hopefully you can see where this is going, because hopefully you recognize this form of an integral. It is, as you guessed, a logarithm, right? So here's that same line again, and here is the actual now carried out integral. So the first integral just becomes the natural log of delta t2 over delta t1. And the right-hand side of the equation just becomes minus UA over 1 over CH plus 1 over CC, right? Because this was basically just a constant, and then the integral of dA. And A is just the heat transfer area between the hot stream and the cold stream, right? So nothing spectacular about that. Okay, so now we're going to replace CH and CC by substituting in this equation here, which is actually two equations, right? We've got this equals this, and this equals this. So we plug that in here, and now we're just cleaning things up, right? So I recognize that these Q's are the same Q, so I'm going to pull them both out. And then I'm just going to rearrange all of these temperatures so that I have all the inlet temperatures bunched together and then all the outlet temperatures bunched together, right? Which makes sense because those are my delta T's, right? So delta T1 is high temperature at the inlet minus cold temperature at the inlet, and then delta T2 is the high temperature at the outlet minus the cold temperature at the outlet. So I just got to rearrange a bunch together in that way. Okay. Whew. Um, Same equation as I had before, right? Just here for reference. Um, so if I'm looking at this and I'm trying to identify what is delta T1 and what is delta T2, well, delta T1 is just T of the hot side at the inlet minus T of the cold side at the inlet, right? So I've got that written here, both in terms of numbers. If you call this inlet station 1, then this expression is correct. If you call this station I, then this expression is correct, right? They're identical, interchangeable. Just want to make sure that I'm using notation that everyone is comfortable with. And that's going to equal delta T sub 1. And the same thing is true on the outlet side, right? So here on the outlet side, we've got the temperature of H2 minus, the temperature of the hot stream at station 2 minus the temperature of the cold stream at station 2, right? It's this temperature difference. Station 2 is the outlet, so HO for outlet, CO for outlet, and that's just going to equal delta T2. Whew. Okay, so now that I've got all that done, I can go back to my original equation. I can plug all this in terms of delta T1 and delta T2. So again, these are the temperatures at the inlet and the outlet. And the reason that I want to do that is because up until now, I've had to deal with the local temperature along the heat exchanger, which I don't actually know, right? I know it at the boundaries, but I don't know what it is along the heat exchanger itself. So I'm basically substituting all this for that so that I can now make a problem solvable. And so there it is. So Q dot is equal to UA times delta T2 minus delta T1 divided by natural log of delta T2 divided by delta T1. Okay. And I can now finally compare this guy to this equation and realize that this thing, which I'm calling TLM for log mean temperature, is just the mean temperature that I've been looking for this whole time, right? So through that comparison, I'm able to eliminate everything else and recognize that this is sitting all by itself, and that is equivalent to this guy, which is from the equation that we started talking about when we were interested in heat transfer and average temperatures. Okay, so the big kind of takeaway conclusion is that delta Tm is equal to delta T log mean. And so this equation that I've given you now actually represents your solution approach for these types of LMTD type problems, right? It's you've just got to figure out what delta T is and plug it in, and then this will pop out. Right. Okay. So it turns out just because of the nature of the log mean temperature difference, delta T2 minus delta T1 over the natural log of delta T2 over delta T1 is actually equal to the inverse, right? So if I take delta T1 minus delta T2 over the natural log of delta T2 minus or over delta T1, these two will be mathematically equivalent with each other. So just a little aside mathematical trick that you might find helpful as you're trying to solve in the future. Now, not sure that anybody knows this reference. I might be dating myself here. This is Butthead from Beavis and Butthead, which was a MTV cartoon that ran when I was a teenager. And so we basically have Butthead here saying, "It won't happen again," right? And I'm trying to do his voice. So, like I said, we don't ever have to do this again now that we've done it once, because this equation and the definition for log mean temperature difference is true for all heat exchangers. We just have to find what delta T2 or delta T1 is. And that'll give us the log mean temperature difference. So there's a whole other type of LMTD analyzed heat exchanger, which is the counterflow heat exchanger. I could go through all of this insanity again, but I'm not going to because I don't have to because I've already solved it once and we never have to solve it again now that we've seen it once. So there's only one slide on counterflow heat exchangers instead of 10. So for counterflow heat exchangers, the cold and hot streams run in opposite directions, right? So notice we've got the fluid entering, the hot fluid entering from the left and leaving from the right, and we've got the cold fluid entering from the right and leaving from the left. So they run counter to each other. um, for this case, the delta T change in temperature remains similar for the entire traverse of the heat exchanger, the entire X distance. So you can actually see that here in this figure. We've got distance along the heat exchanger in the X-axis, and then we've got temperature in the Y-axis. And you can see here's the cold stream, and here's the hot stream. And as you would expect, the hot stream is getting colder, the cold stream is getting hotter. Um, and they're getting colder and hotter by about the same amount. And so that's what this means. Delta T remains about the same, right? So that's we'll see later. That's very helpful. The other thing is that you can run into a situation where the outlet of the cold stream is actually hotter than the outlet of the hot stream. And now this seems counterintuitive. It was actually impossible before. Where is it? Yeah, it was impossible before in parallel flow heat exchangers. The best you could do is make these two temperatures equal to each other. But because these are in counterflow, these fluids are in counterflow, you could actually get a situation where this spot, TH out, is a lower temperature than this spot, T cold out. And you can actually see that here. So I grabbed this figure from just another source, and they actually did it, right? So this line that I've added is just for me for emphasis, but you can see here, here's the hot stream, right, getting progressively colder, and here's the cold stream getting progressively hotter, and it just so happens for that particular heat exchanger, whatever it was that they were analyzing, that T cold out exceeded the temperature of T hot out. So just a real world example of how this is true for counterflow heat exchangers, but not for parallel flow heat exchangers. Okay, the same equation that we got for the parallel flow heat exchanger works for the counterflow heat exchanger. All we need to do is get the correct values for delta 1 and delta 2 and plug those into the expression for log mean temperature difference, and out will pop a delta T log mean, right? Which we can then plug in to our heat transfer equation for heat exchanger and figure out Q, which is usually the ultimate goal. Okay, so we need to define delta T1 and delta T2 for counterflow heat exchangers. It turns out that these are different from parallel flow heat exchangers, so be careful. Make sure you know what kind of heat exchanger you're dealing with and what the delta T1 and delta T2 definitions are, or you can actually plug in the wrong thing and end up with a totally wrong answer. I highlighted the differences here in red, right? So this is TH1 minus TC1, same as before, right? TH1 minus TC1, except here, this is TH of the inlet minus TC of the inlet. Here, it's TH of the inlet minus TC of the outlet, right? Why? Because we're talking about the temperature difference at station 1, right, which is there, or temperature difference at station 1, which is there, right? This is now the outlet of the cold stream, not the inlet of the cold stream, which is why this has changed. Same is true on the other side, right? It's the same equation, TH2 minus TC2, right? So we'll go back, right? TH2 minus TC2, same equation, except C2, TC2 is different because here we are at station 2, and that is now the inlet of the cold side instead of the outlet like it was in parallel flow. So just, be careful, mind your inlets and outlets. Okay, so once I know those temperatures, I can plug them into delta T2, delta T1, and that gives me delta T log mean. And then I can take that and plug it into my UA equals delta T log mean equation and get the heat transfer between the hot stream and the cold stream. So we've got all the tools that we need now to deal with LMTD, parallel flow, counterflow heat exchangers. The one thing that I want to mention is that for the same inlet and outlet temperatures, the same conditions, it is true that delta T log mean in counterflow is always greater than delta T log mean in parallel flow. Hence, the required UA to, excuse me, the required UA to get some needed Q dot is smaller for counterflow than it is for parallel flow, right? That's basically always true. So this begs the question, if counterflow heat exchangers are fundamentally better than parallel flow heat exchangers, why in the heck would anybody ever build a parallel flow heat exchanger if counterflow is always better? And when I say better, what I mean is that the delta T log mean for counterflow is greater than the delta T log mean for parallel flow. Hence, UA required to get the same needed heat flux is smaller for counterflow than it is for parallel flow. And then you get the additional benefit of, for a counterflow heat exchanger, the possibility of increasing the cold stream outlet temperature above the hot stream outlet temperature, whereas you cannot do that for parallel flow heat exchangers. So why would you build one of these things, right? If they're basically inferior to counterflow? Well, there's a couple of reasons, and these are not mentioned in the book. The book actually doesn't talk about this at all. So the first reason is that it is often desirable to minimize the thermal stress. In other words, you want all of the metal on one side of your heat exchanger to be hot and all of your metal on the other side of your heat exchanger to be cold, and for there to be a gradual temperature change along the axis of your heat exchanger, which is far more likely to happen in a parallel flow heat exchanger than it is in a counterflow heat exchanger, right? So you can actually see that here, right? Like really hot, a little hot, really cold, a little cold, right? Versus like really hot all on one side, really cold all on the other side. So you might need that if you have a heat exchanger that is made out of some sort of very brittle material, something that's glass or ceramic. I don't do it in my fluids class, but I actually have a little it's actually a still, but it's a chemical still, right? Not for making alcohol per se, but for distilling chemicals. And all the heat exchangers, because it's chemical lab equipment, all the heat exchangers are all made out of glass, and they're all parallel flow, all specifically for this reason, is because we're trying to minimize the thermal stress in those heat exchangers because glass is very brittle and breaks if you put it under substantial thermal stress. You might also have a very large piece of equipment and you're worried about thermal expansion, right? So better to have a parallel flow than a counterflow heat exchanger if you're worried about thermal expansion and things getting kind of pushed out of spec, because you have these large pieces of metal that are thermally expanding and thermally contracting, and all of a sudden their tolerances go to hell because they've changed shape so much or changed size so much that they no longer fit, for example, in the shell of a shell and tube heat exchanger. Another reason you might use parallel flow heat exchangers is both piping connections are going to be on the same side, and you might want to do that to simplify, shrink, or enable access to your heat exchanger. So you see this a lot in like automotive radiators, right? Both the inlet and the outlet for an automotive radiator in the same spot, just because that's the spot that's easy to access. And so even though radiators are, less efficient because they're parallel flow, it's very easy to get to the inlet and the outlet because they're right next to each other. So that's a reason. You also see this a lot with building retrofit installations. If somebody's adding a new hydronic system to a building, like it actually saves money in the long run to run all the pipes to one place instead of running one big long pipe to the other end of the heat exchanger. In the end, it's just easier and cheaper to save money by using less piping. And so a lot of times people will just retrofit with heat exchangers that are parallel flow rather than counterflow, so they can just bring all the fittings into the same spot, right? So Number three is built-in passive thermal regulation, right? So this goes back to this idea of for a counterflow heat exchanger, TC of the outlet can be greater than TH of the outlet. You might not want that, right? You might want some passive thermal regulation that is specifically built in to avoid the temperature of one of your streams getting too hot or getting too cold, right? So you see this a lot in preheaters, in freeze protection like refrigerators, and then also in viscosity control, right? You don't want the fluid to get too cold because it gets thick and it's hard to pump. You don't want it to get too thin to get too hot. And so you take advantage of this fact that the heat exchanger, parallel flow heat exchanger, simply cannot make the fluid any hotter than the hot stream temperature to your advantage as a passive thermal regulator. And then finally, it's oftentimes it's just cheaper and simpler to manufacture a heat exchanger that has all of its ports on one side. So you see a lot of disposable and plastic heat exchangers where the inlet and the outlet are on the same side. This is also true of like historical systems. So like locomotive boilers and heat exchangers that were made in like the 1850s, 1860s. Their manufacturing techniques were far less sophisticated than we are now, 150 some odd years later. And so just for like the sheer like we need a heat exchanger, can we do it factor of 100+ year old heat exchangers, sometimes you see parallel flow heat exchangers as opposed to counterflow heat exchangers, just because the manufacturing technology of the historic equipment didn't facilitate anything else. So a couple of reasons why you might see this in the real world. You might actually design one on purpose to take advantage of these benefits for parallel flow heat exchangers. Okay. There's a couple of special operating conditions that you need to be aware of because these will mess up your LMTD calculation. You can still use LMTD, but you just have to be aware of what's going on. So the three cases are the situation where the thermal mass of the hot stream is greater than that of the cold stream. And so we see that here, right? So this is a situation where this guy basically has an infinite heat capacity, and this guy does not. And so the temperature of the hot stream remains constant throughout the heat exchanger, while the temperature of the cold stream increases to meet the temperature of the hot stream. This occurs both when these C's are, very, very significantly mismatched. This C can be very high compared to this C. The place where it happens kind of most obviously is if you have a fluid that is condensing from a vapor to a liquid, changing phase. If it's changing phase, it stays at constant temperature, and its ability to absorb thermal energy is basically infinite, right? So, so I say here, CH basically goes to infinity for the case you have a condensing vapor, right? Vapor going from, or a fluid going from a vapor to a liquid, right? Constant temperature. So in this case, you should use Q dot equals M CP delta T to do your Q dot calculations, as opposed to trying to use the LMTD method. Okay, the same is true on the flip side. So you could have a situation where it's now the cold stream, which has a significantly higher thermal mass than the hot stream. And in that case, the cold temperature remains constant while the hot temperature comes down to asymptotically meet the cold temperature. This occurs if the cold fluid is evaporating or boiling, right? So you see this a lot in evaporators and boilers for power plants. And just like the case here where CH basically goes to infinity for all intents and purposes, the same is true here, is that CH of the car, CC of the cold side will basically go to infinity if you're changing phase. And so here you're going to want to use Q is equal to the hot side mass times the hot side CP times the hot side temperature difference, because the hot side is the one that's cooling down and the cold side is just absorbing all that thermal energy without budging, without changing temperature. Okay, the third situation is if you have a counterflow heat exchanger where the two C values, thermal masses, are matched. So CH is equal to CC. In that case, the temperature difference is constant all the way through. So delta T1 is equal to delta T2. And if we go back to the log mean temperature equation, right here, you can immediately see the problem, right? Which is you get 0 on the top, right? T2 is equal to T1, delta T2 is equal to T1. So 0 on the top, and then in the denominator, you get a logarithm, which is basically the logarithm of 1, which is 0. So this is like delta TLM is equal to 0 divided by 0, right? So it's a mathematical mess. So remember, the reason that we derive this is because if we go all the way back, what we're actually looking for, if I can find it without going too far. No, I went too far. What we're actually looking for is this, right? An appropriate mean temperature difference for our heat exchanger. Well, fine. If the change in temperature is the same all the way down the axis of your heat exchanger, you no longer need a log mean temperature difference, right? It's just the delta T from the hot side to the cold side. So in this case where we've got, whoops, too far. There you go. Where we've got delta T is the same all the way through the heat exchanger. Those two delta T's are equal to each other, and they just become the temperature that you use for the log mean temperature difference or the mean temperature difference in your heat exchanger equation. Okay, but got to be aware that that's a possibility, because you could, you guys will see. We'll do an example where hint where this happens. Okay. Speaking of examples where this happens, here we are. Okay, so let's do an LMTD example. When we do the next lecture on the effectiveness NTU method, I'll walk through an example or two of effectiveness NTU. But right now we're talking about LMTD, so let's do that. Okay, so we have a counterflow heat exchanger which heats fluid A. Fluid A happens to be the cold fluid, and it's flowing at 2.4 kilograms per second. It has a specific heat capacity of 0.8 kilojoules per kilogram Kelvin. And fluid A enters the heat exchanger at 0 Celsius or 273 Kelvin. I borrowed this problem from another heat transfer book, and I changed all the temperatures to Kelvin because I love to do that for you. So you should do that as well. If you ever encounter in heat transfer fluids that are in Celsius, you should immediately change them to Kelvin, because now we're taking ratios and products and like derivatives and division, and right, and if you do that with not absolute temperatures, you're going to your math is going to get screwed up, right? So just make sure that you convert everything to absolute temperature, do all your math in absolute temperature. If you need to at the end, convert back into Celsius, but please just do everything in absolute temperature. I think I've said that a bunch of times, and I'm going to say it again. Okay, so 273 Kelvin and leaves at 673 Kelvin, which I think is, what is that, 400 degrees Celsius? Yeah. Okay, so this cold fluid in the heat exchanger is heated by hot side fluid, fluid B, which is flowing at 2 kilograms per second with a specific heat of 0.96 kilojoules per kilogram Kelvin. And that enters the heat exchanger at 973 Kelvin. And so we're told to determine the percentage increase in heat transfer surface area required to increase fluid A output temperature from 673 Kelvin to 773 Kelvin. So an increase of 100 degrees Celsius or Kelvin. Okay, so let's make our standard assumptions. So these are just the standard heat exchanger analysis assumptions that you should always make unless you're told otherwise, right? You should always make when you jump into a heat exchanger problem. So we know that the heat exchanger we're going to assume that the heat exchanger is insulated from the surroundings, so we don't have any other heat transfer out other than the heat transfer that's internal from the hot stream to the cold stream. Axial tube conduction is negligible, right? Remember, we talked about that. You don't have any heat transfer in the axial direction along the metal of the tube. The potential and kinetic energy changes are small. Talked about that. Fluid properties and specific heats remain constant. You kind of need that, right? Or you can't solve a lot of these problems. And then the overall heat transfer coefficient is constant. for this arrangement. Okay, so um, I'm going to start every energy thermal fluids problem with a sketch. Here's my sketch. This is my counterflow heat exchanger. I have, yeah, cold fluid entering in the center, and I have hot fluid in the shell on the outside. I know the cold fluid entering temperature is 273. I know its exiting temperature is 673. I know the counterflow, the hot fluid is entering at 973. I don't know the temperature that it's leaving, so I'm gonna have to find that. And so let's jump into that. So first thing I'm going to do is try to find this outlet temperature for the high temperature side. So I'm going to use the green control volume that I've drawn here to find the outlet temperature for the hot side. Okay, so presumably you took thermo. If you guys took fluids with me, you've seen me do this before. I try to write out the entire first law of thermodynamics in all of its glory every time I solve one of these problems, both because I think it's just important to see where all the terms are and the terms that you're crossing out. And also, I think the most like cathartic, like therapeutic thing in all of mechanical and aerospace engineering is crossing terms out of equations that you don't need. So I love to do that. So we know that our heat exchanger is adiabatic, so those terms are gone. We know that there's no shaft work, right? I don't have any shafts crossing the system boundary, nothing turning. So shaft work in and shaft work out are zero. I made the assumption that everything is happening in steady state, so the um, energy term, time-dependent energy term is gone. And I also know that kinetic energy and potential energy are negligible. So the velocity term, kinetic energy term, and the elevation potential energy term in both the outlet and the inlet, all that disappears, right? So what I'm left with is this guy. So the sum of m dot out times h out minus the sum of m dot in h in is equal to 0. And then I'm just going to do a little bit of rearranging, right? So remember that H is CPT for liquids and gases for fluids. And so I'm just using that relationship CPT equals H. Oh, I should mention, right? H, this is enthalpy, right? So I'm using the fluids or the thermodynamic version of enthalpy. The book used capital I, but sorry, I'm using my thermo brain here for this. So just be aware that that's what I mean by H. This is not high temperature H. This is enthalpy H. Okay, but these guys become these guys, right? So they're equal to each other, and I'm just pulling the constant specific heat for each of the fluids out, leaving m dot Cp times the temperature difference for the cold fluid. Same for the hot fluid. Okay, so now we need to find, right? So the thing that we ultimately need to find is this kind of area ratio required to change the outlet temperature. But before I do that, I need to find the uh, the outlet temperature on the high side. So there's going to be two cases. So one is the case, we'll call it case one, where the cold side outlet temperature is 673. And then we were told that case two is the temperature where the cold side outlet is increased by 100 Celsius up to 773 Kelvin. And so for those two cases, I'm going to solve for the hot stream outlet temperature. How do I do that? Right. I'm just taking this guy, I'm rearranging it, solving for TH out. Right. So here's me doing that. And then I'm going to plug in the numbers. So here's me plugging in all the numbers that I calculated from before. And what pops out is that TH out for case one is 300 Kelvin, sorry, 300 Celsius, 573 Kelvin. And for case two, where that outlet temperature is a little bit hotter, it pops out as 473.15 Kelvin. So 100 degrees colder than case one. Okay. We know that U is fixed, right? Because we made that assumption overall heat transfer coefficient is constant. And so I want to just apply my LMTD method for counterflow heat exchangers to find the area in both cases. And then if I take the ratio of those two areas, that gets me to what I'm trying to solve for, right? Which is the percentage increase in heat transfer surface area required to increase fluid A output temperature. So I'm just looking for a ratio of those two areas, area for case one versus area for case two. Okay, so what I need to do, at least what I think I need to do, is find heat flux. And so I'm going to use my heat flux LMTD equation here. And I need to plug in these delta T's, and to find the delta T's, I need to know what the temperature is, what the delta T is for these two cases, right? So for case one, I'm going to plug in the 573 that I found for TH out. Right, so here it is, TH out, 573. So I get 300 Kelvin there. And then for TH in minus T cold out, delta T1, I also have 300 Kelvin. So this all of a sudden is starting to look a little fishy, right? But I'm going to just imagine that I have not seen that these two delta T's are the same, and I'm going to kind of carry this through, and you'll see what happens. But this should be an alarm, right? This should be an alarm that these two temperatures are the same, right? Hint, remember, we just talked about that. Oh, okay. Case two, same story, right? So I'm just going to plug in my known 473 Kelvin, which is my TH naught for case two. It's right here. And I go through and I end up getting 200 Kelvin as my delta T1 and my delta T2, right? Alarm bell should be going off now because those temperatures should not be the same. If they are, I need to do something special. But I'm going to assume that I don't know that yet. I'm just going to make my way through and we will see what happens, right? So I now have my delta T1 for case one, my delta T2 for case one, my delta T1 for case two, my delta T2 for case two. I can now plug in these temperature differences into my LMTD equation to back out Q. I need Q to be able to figure out the area difference, which I'm going to take a ratio of the areas to find that percentage. So what happened? I started plugging in these values for case one, and oh my God, I got 300 minus 300 divided by ln of 300 divided by 300. That's UA times 0 divided by ln of 1, which is 0. I'm basically 0 over 0. This is like the end of the universe, right? So catastrophic. But remember, right? We talked about this as a special case. This is a counterflow heat exchanger where C sub H is equal to C sub C. And you can actually see that. I didn't do it, but you can see that if you multiply the values together, right? So 2.4 kilograms per second multiplied by 0.8 is the same value as 2.0 multiplied by 0.96. The book specifically chose these numbers so that they would match up and give us the same capital C sub H and capital C sub C, which is now this situation, right? Where I've got capital C equal to capital CH. And what that means is that these two curves are separated by precisely the same amount the entire traverse of the heat exchanger, which means we don't actually need LMTD. We just need to know the temperature difference, and we can plug that into our mean temperature difference for the heat exchange equation. Okay, so that's what I say here. Counterflow heat exchanger, C sub H equals C sub C, so delta T1 equals delta T2 equals delta T long mean. So I could just use that. I still need to find Q, and I can find Q independent of the geometry by just plugging into my first law expressions that I derived way back in the beginning, right? So the thing that I actually solved for was let's see. These are my two cases, and you know what? I didn't actually. Okay, I'm like looking to find my it's this value and this value, right? But I didn't actually even use those. Right? Because they're not in there, to solve for these heat transfers. So for case one, MCP delta T is 768 kilowatts, and for case two, MCP delta T is 960 kilowatts. Okay, so now I have all the information that I need, right? So remember, we're seeking a percentage increase in heat transfer surface area to increase fluid A's output temperature. We know for case A, or sorry, for case one, that the heat flux is equal to UA times delta T M for case one. I left the log mean in there because that's how the equation is actually written, but this is just delta T mean, which is that constant value that we calculated. Case two, same equation, right? Delta T mean for case two. And I know that delta T for case one is 300, delta T for case two is 200. Uh, yeah, Q dot for case one is 768. Q dot for case two is 960. And so I'm now going to just take the ratios of the heat flux calculated for case two and calculated for case one. And what that gives me is a quotient, a ratio of UA delta T for case two divided by UA delta T for case one. The U's are the same, so those cancel. And what I want to isolate, remember, is that ratio of areas. So I'm going to move everything to the other side of the equation to leave the ratio of areas untouched. So I have Q dot 2 is equal to delta T of case 1, all divided by Q dot 1 times delta T for case 2. I know all those values, right? I've got them all tabulated here, so I just plug them in, and what pops out is that Q2 over Q1 is equal to 1.875. And what that means is that to facilitate this 100-degree temperature increase in my heat exchanger, I need to increase the surface area for case 2 by 87.5% above the existing surface area in case 1. Right? So that's the conclusion. I checked it out against the equations, solutions in the back of the book, and it agrees. So we are good. Okay, that brings us to the end of this presentation. Thank you for your time and attention, and keep your eyes open for the next lecture in the heat exchanger module, which is the effectiveness NTU method. Cool. All right. Thanks, and I'll see you soon.